Okay, then you have something called apparent depth. So suppose if you want, you folks can try this experiment, or I'm sure you must have tried it in your home, right? So if you take a small beaker, if I keep some kind of a small object, something like a coin, right? Let's say this is a coin kept inside the beaker. So initially you will be seeing that the coin is there, but the moment you fill this with water, how does it feel like? It feels like the coin has come a little bit up, right? So what you are saying is correct. There will be some sideways shift also, but mostly it will be like, it looks like it has come a little bit, right? Even though the coin is still sitting in the bottom. That is what we call as apparent depth. This is the real depth. But if the coin looks as though it is here, then we call that as apparent depth. Apparent is not the real one, right? So apparent depth. So if I consider a ray of light coming from the coin, right? It flows like this. Okay. So let's say I'm standing here. So this is my eye. That means the ray of light coming from here, this is compared to here, this is rarer or denser? Denser to rarer. So instead of going straight, what will happen? So this is a normal. So denser to rarer, away from the normal. So that means instead of going this way, it will go this way. Okay. So that means this is how it is supposed to go, but then it's going to go away from the normal. The ray of light which goes straight, it will go straight like this. This is a very interesting phenomenon in refraction, right? Very often we overlook this and we forget to see, importance of this. When a light is going straight, right? Let me keep this slow. So if I put the ray of light, right, like this in an angle, you will see that it is kind of going, it will be refracted. Okay, again, as I said, you have to do the experiment in a paper, only then you will be able to see the ray of light, right? Otherwise it's hard for you to see it. Yeah, we'll try to do that after this. Okay, so you see, if I put it a little bit closer to the thing, you can see the ray of light going in, right? So in this kind of situations, when you have an angle, you will see that the light is getting refracted, changing, right? But suppose if I put it straight like this, do you think will there be any refraction? No. If you put straight 90 degree, right, there is no refraction, it just goes straight. Okay, even though the speed of light is reduced, still it will be going straight. Okay, so that's why, when something is going straight like this, it will come out straight, whereas if it's coming in an angle, then it will be refracting. Okay, following that. And one important thing is you are seeing it, which means the light rays are coming from the coin. So you have to show the light rays coming from here, not from this side. Okay. And this arrow is not required, you can leave it like that, because it's understood that it is coming from the coin. Okay. So carefully listen. So a person who is seeing this ray, right? This ray is coming like this. Okay. So because of the refraction, it got bent like this. So somebody who is seeing it from here, right? He will be thinking that the ray is coming from here. So it looks like it's coming from here. You follow what I'm saying? So that's the reason why we think that the coin is actually looking something located here. Again, we are doing it for one single ray, so the same thing happens for all the rays. Okay, everyone following this? How I drew this? This bent ray, right? You have to extend it, and that will show where it is forming the image. So this is the actual object, this is the image. So now going back to this is my angle of incidence with the normal, right? So this is angle of incidence. What is this? Angle of refraction up to this point, right? Not up to this one. So if this is confusing, you can remove this. Only when you are drawing this, you need to have that. You have to talk to yourself. You have to say, okay, the light is supposed to go this way, but then since it is denser to rarer, I have to say that it is going away from the normal. Okay? If you don't talk it and do it, you will be making mistakes. So every time you have to ask yourself, okay, rarer to denser means away from the, towards the normal. Denser to rarer means away from the normal. If you do that, you will not make mistakes. Yeah. Good question, but in reality you will still see a little bit of a because your eyes are not perfectly perpendicular. No matter how much you do it, right? There will be a little bit of a angle. I will draw that and show you. Let's just say. Okay. So even this angle which we are showing here, right? It's an exaggeration. In reality, it's not going to be this big. So in reality, the way this is going to look is this is a coin, this is a water, straight line. So the refraction is going to happen like, so even this one is an exaggeration because your eyes are something like this, right? If the ray is going here, your eyes is not going to capture it, right? It has to go through this small area. So this entire thing is actually the size of your eye. You following what I'm saying? So this is more like an exaggerated diagram, just to make it easy for you to show the angles. Okay. In reality, it happens in a very small way. So maybe if I want to draw it a little more accurately, it goes something like this. Yeah. So coming back to the question, not all the rays are coming perfectly perpendicular, right? So maybe one ray is coming perpendicular, but the other rays, because of your size of your eye, so it's going to be having some kind of a angle. Okay? So in which case, the effect may not be as much as this much, like this, but still you will see a little bit of a rays in the coin. Okay? Or to put it the other way, if you really want to see the coin raised up, you have to see it in an angle. If it is perfectly 90 degree, probably the effect will be very low. Yeah, yeah, glass, water. Then it will be raised much more. It will look like as though it is raised more. No, both are higher refractive index. Right? So we will talk about that. You will get some problems like that. So because this itself is forming an image here for this, it will form the image for the next one. So it will be much more higher than this. Okay, coming back to this, this is my angle of incidence, this is angle of refraction. If this is R, what can you say about this angle? This is like a straight line I told you. So this is perpendicular. So what can you say about this angle and this angle? Both are same, right? If this is I, what can you say about this angle? Can you see the Z here? So alternate angles, right? This is I, this is also I. And this I am going to call it as real depth, RD. Instead of calling it as H or Y and all those things, let's call it as real depth, RD. So that you don't have to remember what it is. Okay. Here also that's why I call it as lateral shift. This height is what I want, which is your, what do you call this? Apparent depth. So let's call it as AD. And again, simple trigonometry. So I want this one, right? So look at this triangle and this triangle, right? So all this entire chapter you have to keep on looking the triangles. So I know this entire length. So let me redraw this again. So this is I, this is RD. So how to find this one? Is this adjacent angle or opposite side or adjacent side? Opposite. So that means sin I is equal to, let's call this as x divided by RD. So x is equal to sin I into RD, real depth. Okay. Now look at the other triangle. So suppose let's say I draw the other line here. This is R. This is my apparent depth AD. So now tell me, sin R is equal to x by apparent depth. Am I making any mistake here? Okay, sin means opposite by hypotenuse, right? How come I am taking this one? Are we not supposed to take this one? But in this particular derivation, right, we look at this and this line and this line. What can you say about this line and this line? They're almost same. So I told you, it's just an exaggeration to make it easy for you to understand the diagram. Okay. In reality, it's going to be very, very close, which means this hypotenuse and this side is going to be almost the same. So that's the reason instead of taking this length, I'm saying this is going to be very, very close to this length. Okay, it's an approximation we are using. Is that clear? Anybody having doubts? So you have to take down this drawing also to understand that the L1 and L2 are almost the same. So that's the reason why we are not taking the hypotenuse. Instead, we are taking this one. Why? Because it's easy for us to measure the height rather than measuring the hypotenuse. So here also I forgot to tell you, whichever is given here, these are things which you can measure it, which means all these things are known. Similarly, so I want AD, so AD comes on this side, x by sin R. What is x? Sin I divided by sin R, right? So that means apparent depth is equal to sin I by sin R into real depth. But please listen here. This is angle of incidence or refraction? Incidence. This is refraction. So where is the refraction happening? Air or water? Air, right? So that means sin I by sin R is equal to, is it NGA or NAG? NAG, because the refraction is happening in the air. So air with respect to glass. Okay. So that means sin I by sin R is not NGA. This is where people will make mistake. Okay. That means sin I by sin R will be NAG. But then generally speaking, right, I know the refractive index of water, it's a constant. Okay, which means it is NGA, not NAG. That means it will be a reciprocal. So I can say this can be written as 1 by, So RD divided by NGA. So refractive index of water is something like 1.33. Okay, I should have written as W, right? G for glass. This is water. Okay. Some books will use 1 and 2, but I prefer to call it as AGW. Okay. Because most of the time we will be using only these three things. So for water it is 1.33. Why 1.33? Why should it be greater than 1? Speed of light in vacuum divided by speed of light in the medium. So which one is bigger? Vacuum, right? That means obviously it's going to be greater than 1. Are you following that? For glass it will be 1.5, approximately 1.5. Okay. For water it is 1.33. So now tell me, this is the real depth divided by bigger than 1. So the apparent depth will be smaller or bigger than real depth? Be smaller because greater than 1. So you have to do this kind of double checking. That's all. So this is what is called apparent depth. Okay. So basically apparent depth means the depth of the image. Any doubts here? Why I did this kind of conversions? I don't think they'll ask you too much of derivations here, but this understanding is important for your numericals. Okay, it's there in your textbook.